Hi, good morning. Speaker today. I'm Likai Chen. She is currently an assistant professor of mathematics and statistics at Washington University in St. Louis. She got her PhD degree from University of Chicago, supervised by Weibiao Wu. Her research interests are time series, high-dimensional statistics, and maybe machine learning theory. So because of the frigid weather, actually a lot of flights were canceled in the past 2 days, and her flight was delayed as well. But she eventually arrived this morning at 2 a.m. I guess it has been a very difficult morning for her. So we feel very lucky because none of us wants to miss your interesting talk.
Thank you for the introduction. So today I will talk about L2 inference for change points in high-dimensional time series via a two-way mode sum. So this is a joint work. Oh, wait. So. That's not working. Okay, this is a joint work with Jiaqi Li, Weining Wang, and Weibiao Wu. So for about multiple change points detection, it mainly falls into two kinds of problems. One is about model selection, the other is about hypothesis testing. So model selection is to say that we treat those change points as some additional parameters, and we try to use various model selection methods to find the one that is best suitable for the data set. Another main category of multiple change point detection is about testing. So here I list some, but not all, of those commonly used approach. So the first one is related to exhaustive search, which is essentially to search all the potential break locations. So such method is computationally expensive. There are some dynamic algorithms invented to speed up the procedure. Another popular approach is based on binary segmentation. Well, today I will focus on moving sum statistic. So let me briefly introduce what is the idea of moving sum. So here is a picture. So suppose we observe a univariate time series. So this is just a one-dimensional time series. And the idea of moving sum is that we consider a moving window. So here, this red box, so those red lines corresponding to a window. So we move the window from the beginning to the end. So we go over all the potential points. And for each window, we look at the left average and the right average. So if there is a break at certain points, so if there is a break here, then you can imagine the right average and left average, the difference will be relatively large. And if there is no break, their difference will be relatively small. So this is the rough idea of moving sum statistics. So by changing the window, so we change the window from the beginning to the end, then we go over all those points in the middle. And if there is a break, then we can find that. So this is the idea. So for such kinds of test statistics, the advantage is it's very computationally efficient. So you can see that the computational cost is very low. It can be very fast. The downside is there is some parameter like the bandwidth need to be selected. So now let's talk about, so this is about one-dimensional time series. So when it comes to high-dimensional time series, a question is how can we tell the signal from a lot of series? So here, this is a motivation example. So here I draw a picture of 300 stocks over 252 months. So it's hard to tell through bare eye that whether there exists any breaks. So based on this plot. So that is to say, when the time series becomes high dimensional, it might not be that easy as previously, which is one dimensional, to tell whether there exists any breaks in the middle. So that is to say, how can we aggregate the information across these high dimensional time series to help us detect the break locations? So this is one main challenge in high-dimensional time series change point detection. So how can we aggregate the information across different locations? especially when the signals are relatively weak for each coordinate. And when, well, there's a lot of signals through the series. So to get around with this issue, well, we would like to propose an L2 aggregate Moson test statistic. So why we consider the L2 aggregate Moson test statistic? So here is a picture to illustrate the idea. So previously, there is L infinity based test statistic. So here we consider L2 type statistic. So L2 is to say that we consider square and taking the summation over all the coordinates. So the first picture is corresponding to P equals to 50. The second picture is P equals 100. The blue line corresponding to the test statistic, the power of the test statistic based on L infinity norm. So L infinity norm is to say, to aggregate the information across different locations, we look at the maximum. So essentially, we look at what's the largest difference. And L2 is to say that we look at the square summation. And based on the picture, it can be seen that, well, when the, so the X label corresponding to the proportion of dimensions with jumps. So this picture tells us that, well, when the proportion of dimensions with jump increases, so that is to say, if more series jump simultaneously at the same time points, if we consider an L2 based test statistic, the power will increase very fast. However, if we consider L infinity based statistic, L infinity is to say to look at the maximum, then the power does not, well, almost doesn't change. Well, this is the intuition behind this is because when we look at the maximum norm, we only care about the largest signal across different locations. But if we look at the L2 based norm, then we aggregate all those signals together. So when there's more proportion of series that jump simultaneously, then we potentially it's easier to detect the break locations. So this is, so from the picture, you can see that if the proportion is greater than, say, in the first example, 0.1, then the L2 is more powerful. And in the second example, when the dimension P is even larger, then the proportion needed for L2 statistic to be better is even, the proportion is even smaller. So this is the main reason that we consider L2 type of statistic here. So now let's talk about our model setup. So this is a relatively simple model setup. Later on, when I talk about cross-sectional dependence, I will introduce a slightly more complicated model to introduce the cross-sectional structure. So here, let's just focusing on this YT here. So YT here is a p-dimensional time series. So T can go from 1 to N corresponding to time, and YT is in RP. So each coordinate corresponding to one location. Mu here is the trend, and epsilon T here is the noise. So the question about multiple change point detection is to say that suppose there is K0 change points, and the trend can be decomposed into two parts. One is the smooth varying trend, mu0. The other is the break. So gamma K here. So gamma K corresponding to the break vector, the jump vector. UK here is the break location in time, and K0 is the total number of breaks. For now, for notation simplicity, we will assume the noise to be a moving average. It can be extended to general temporal cross-sectional dependence setup. The notation will be more complicated based on functional dependence measure. So here, let's consider this moving average noise vector. So we assume the noise follows this moving average structure. So here, eta k is the underlying independent innovations, and AK corresponding to the coefficients capture the dependence structure for temporal dependence as well as cross-sectional dependence. And the goal here is that we would like to tell whether there is any breaks. So that is to say, we want to test whether the jump vector all equals to 0. So if there exists any breaks, the next goal is to locate all the break locations and figure out what is the jump size. The idea of this test statistic is very natural. So roughly, it's just well, in order to test whether gamma k equals to 0, well, because gamma k equals to Ju is the left limit and the right limit of the trend. So if you look at the mu t from left and right limit of mu t and left limit of mu t and look at their difference, because Fu here is smooth, so the smooth varying part will cancel out, and only left behind the jump factor. So if there's no jump, then the difference will be 0. And if there is a break, then the jump factor will be gamma k. So based on this idea, well, we just need to estimate the left limit and right limit of the trends. And naturally, we just consider a window with size Bn, and we look at the average from the left and the average from the right, and look at their difference as our gap estimator here. And well, the next question is, because the gap here is in p dimension, so we need to aggregate those information. So we need to introduce a long-run covariance matrix here in order to introduce our statistic, because so here the VI is the difference between the left average and the right average. Now we standardize it by the long-run covariance matrix, the diagonal of the long-run covariance matrix. The reason for that is because for different locations, the vibration of the series might be very different. So in order to prevent some signals be dominated by those series with very large vibrations, we want to standardize each series by its long-run standard deviation, so that they are all about the same scale. So that is why we introduce this lambda, and we standardize each dimension by this lambda inverse. And then we take a maximum over all the windows. So each I corresponding to a time point, and we look at the maximum of them to be our test statistic. And we take this, as we mentioned before, we use this L2 type statistic to aggregate the information across different locations. So this is VIL2, and we take maximum over I. So although the statistic looks quite straightforward, it's just an L2 based Mosan statistic, but previously there's no results about asymptotic distribution for Tn for high dimensional time series. Well, when it's low dimension, the multivariate time series, then we can use invariance principle to find the asymptotic distribution for VI. But when it's high dimension, the problem becomes more challenging. However, we figure out that to find the asymptotic distribution of Tn is not that difficult. So here I will very briefly outline the idea about how to find the asymptotic distribution, and then I will state the results. So essentially, the key idea to figure out the asymptotic distribution of Tn is we only need to rewrite the statistic into this x dimension of xj. What is this xj? Xj, each coordinate of xj is Vij squared centered. So the centered version of Vij. Vij is just the j's coordinate of Vi. And we pile all those i's together as a vector. So xj now is a vector. So through this notation, the previous Tn squared statistic can be rewritten into summation j from 1 to p xj plus some centering term, which is related to the expectation of Vij squared. And it becomes taking the maximum over all the location for this xj. So through this notation, the previous L2 based test statistic again becomes an L infinity type based statistic. And there's various existing results that we can use for L infinity based test statistic. That's the blessing that why we can solve this problem. Especially when they are cross-sectional independent. So if we do not assume any cross-sectional dependence, so we do not assume any dependence between different locations, the xj, they are mutually independent for different j. So this problem can be handled by a result by Chen Zukov et al. 2017. So here I list the conclusion. So based on so based on this setup and under the null hypothesis, we can show that the distribution of the statistic Tn can be approximated by Z, the maximum norm of Z. What is the Z? Z is a Gaussian distributed random vector. And the covariance matrix of this random variable Z follows the similar covariance structure as the summation of xj and centered at C bar. Well, specifically, we can calculate the covariance structure. So, so pay attention here that the covariance here does not depend on anything unknown. Everything is determined when they are cross-sectional independence. So every entity of the covariance is predetermined. And also the centering term does not contain anything we do not know. So we don't need to estimate anything. We know the covariance structure. And because of that, we can actually simulate the Zi. So simulate the random variable Z and find the corresponding quantile. So we can determine the quantile for Z, the maximum norm of the random vector Z based on simulation. And use that quantile to determine the test quantile for Tn squared. Am I going too fast? Okay. Let me know if you have any questions, because there's a lot of notations involved in this discussion. Vn, Vn is so. Oh, Bn. Oh, that's a very good question. I will talk about the selection of the bandwidth later. Yeah, that's very critical. Okay, so this is the main conclusion. And here is the formal statement. So under some regularity conditions, we can show that they're close. So based on these results, we can determine, as we mentioned, we can use this Zk. So Zk is the Gaussian random variable. We can, based on this Gaussian random variable, to determine the threshold R, so that we can control the error at level alpha for whatever alpha that we predetermined. And we shall reject our null hypothesis if our test statistic exceed the threshold. Here is just a result about the power. So gamma k, recall that gamma k is the jump vector. So if the jump vector is not too small, then the testing power will go to 1. I want to say a little bit more about this jump vector. So it seems directly from this expression that we require p, so that the signal to be p to the power of 1/4. But pay attention, this gamma k here for left-hand side is the L2 norm of the signal of p-dimensional signal. So if we assume that all the time series jump simultaneously at level, say, A, then the left-hand side will be A times the square root of p. So that is to say, if for each dimension jump 1/p to the power of 1/4, then, well, this condition will be satisfied. So based on this condition, it can be seen that if all the series jump simultaneously, then when p increases, actually the requirement for the jump size decreases. So this is matching our intuition. Okay, so now we are ready to introduce the cross-sectional dependence structure. So previously, I just put location 1 to p together. So now I want to introduce the dependence for different location. Here, L here. So each notation L here corresponding to one location in a ZV. And L. Oh. Okay. I didn't realize the microphone is not working previously. So the total the total number of bricks is total number of the location is p. So here L corresponding to the location, and we observe time series at each location. So you can imagine there's a lot of sensors on say, let's just consider V to be 2 on two-dimensional space. And well, we observe at one location, so L is one sensor, and we observe over time T. So under this setup, the previous setting can be naturally extended to this this model with this location parameter L. So still we have this trend which can decompose to a smooth varying part and the break part. So here gamma KL corresponding to the break at location L at time UK. So this is just a counterpart of the notation for the break detection. And well, under this setting, so the reason I introduced this setting is because I want to say a little bit about the dependence structure. So the previous result I introduced there, we do not assume any cross-sectional dependence, but in reality, it's hard to imagine there's no cross-sectional dependence between two series if they're close by. So therefore, here we introduce this, again, we introduce this linear dependence structure here. Again, it can be extended to general dependence structure, nonlinear situation, but the notation will be even more complicated. So let's just stick with this linear case. And well, do not worry about the notation here. The key here is that we can, this long run covariance. So essentially the long run covariance between two series. So epsilon TL and epsilon TL prime corresponding to the noise at the location L and L prime. The long run covariance between these two locations can be captured this way. The representation does not matter that much. It's just this sigma corresponding to the long run covariance between these two locations. And as some special examples, if this coefficient is 0 for different locations, if L differs from L prime, then there is no cross-sectional dependence between two noise at the location L and L prime. And if this AKLL prime is 0 for any k larger than 0, then this time series will be temporally independent. So you can imagine this k corresponding to a temporal dependence and LL prime corresponding to the cross-sectional dependence. And here is the assumption we need to impose on the temporal and the cross-sectional dependence. The specific format is not that important. The key idea is that we assume that temporally they decay, they are weakly dependent. So that is to say, if for two time series, well, their time differs, then the dependence between these 2 points will decay polynomially fast. And about cross-sectional dependence, so the interpretation for this cross-sectional dependence is essentially we assume that the long run correlation decays polynomially fast. That is to say, if 2 points, they are relatively far away, then their dependence will be small as well. So if the distance keep increasing, then the dependence will keep decreasing. So this is the weak temporal dependence and the weak cross-sectional dependence that we need to impose in order to get our results for dependent situation. So under this dependence setting, well, we can extend the previous results to the situation when there's cross-sectional dependence. So with such kinds of cross-sectional dependence, similar as before, we can generate a Gaussian random vector with the similar covariance structure as the original random variable, and the distribution of our test statistic Tn can be approximated by the statistic Zk. So the k here again is the normal distributed random variable, and we take a maximum over k. So based on this conclusion, same as before, we can use this conclusion to perform our hypothesis testing. So we can determine whether we shall reject the null hypothesis that there is no signal based on this normal approximation and the corresponding quantile for the maximum k of Zk. Okay. So far, I haven't really. So far, we are always thinking about the situation where all the series jump simultaneously. That is the reason why here, when we consider our test statistic, I aggregate. So here, look at this summation here. I aggregate all the locations. So I take summation over all the L in this potential location Ln. Well, this is not making sense if there's only a subset of the series that exists a break. And also this method cannot tell us anything about, so if there's only a subset of series jump, this result cannot tell us like what is the corresponding locations that exist a break. So if I want to say more than just a temporal break, but also I want to say something about the spatial locations, how can we do that? So here is an example to illustrate that why we care about locations as well. So this is a COVID-19 cases in US, and this is a plot of the case numbers at different locations. So the darker means more cases. So the black color corresponding more cases, the light color corresponding to less cases. So it can be, well, it seems from this picture, the time slice, that the outbreak of COVID-19 cases in different regions differs. And this also enlightens us that we probably want to not aggregate all the locations, but we only want to aggregate locations within clustered.
Are these statewide totals or are they statewide proportions?
Oh, good question. I think it's total. Probably.
California and Texas have the largest population, but Washington State, I don't know.
Right, it's a good point. Probably proportion is making more sense, but I think the picture here is based on the total number. Okay, so because of this cluster, those group, the structure, so we want to modify our statistic based on some subsamples. That is to say, previously we aggregate all the information, over all the locations. Here, probably we want to aggregate informations only within certain subsets. So BL corresponding to a subset. That is to say, we need to, well, introduce some group structure. So B1 to BL corresponding to the subsets that we are interested. And the B1 to BL, they can potentially overlap with each other. So they do not need to be non-overlapped groups. It's okay that this even B1 include B2. So those are the structures. So essentially, if you think there might be some structures there, you can just put a group there. And those groups can overlap or are related with each other. And the statistic now becomes, we look at this summation within this group BL, and then we take a maximum, not just at location, so not just as a location at time. So I corresponding to the location at time, L corresponding to the location for the spatial location. So the reason we introduce such kind of statistics, because if there is only a subset of the series jump, but we aggregate the information over all the locations, then we add too much noise. So if we only take summations over this subset, then, then it will enhance the testing power. So here this is a picture to illustrate what is this two-way Moson. So essentially, previously the Moson statistic is to consider a moving window from time from beginning to the end. So now with this introduction of this two-way Moson, we consider a rectangular. So this and go from all the potential. It can go to all the potential points that we are interested. So this is P1, P2, P3 corresponding to different neighborhoods that we are interested. And the P2, P3 clearly here, they overlap with each other. So we want to consider such a sliding rectangular over all those potential points, and we look at the maximum of it. Here is a comparison of whether we consider the clustered signal or not. So the first picture, so the picture corresponds, the green curve corresponding to the clustered statistic. The right dot corresponding to the aggregation overall. And the first, the picture A corresponding to 90% of dimension that exists jump. The second corresponding to 30%. So it seems like in other cases, if we consider this cluster structure, the testing power is better comparing with the non-cluster situation. So before I talk about the theory related to this clustered structured statistic, I want to talk about the detection and estimation. So that is to say, suppose based on the previous Gaussian approximation results, we already know there is, so the test statistic tell us there is a break. So if the statistic exceeds the threshold, how can we determine the break locations? So here is a very brief outline about our testing scheme. So essentially what we need to do is quite simple. We just collect all the candidates I and L, I corresponding to the time location, L corresponding to the location, BL, the spatial location. And we collect all the pairs such that the statistic at this location exceed the threshold. So the threshold here is determined based on this maximum statistic that we introduced before. So the idea is to say under the null hypothesis, if there is no break, then for all those pairs I and L, the statistic should fall less or equal to the threshold with very high chance. So if the statistic exceeds the threshold, then it means that, well, at this location, time I and this spatial location BL, well, it is influenced by the signal. However, we need to introduce a cleaning step afterwards because the screening step will involve too many points. Why it will involve too many points is because, well, our statistic is based on, so if we recall the statistic, our statistic is based on a rectangular. It's based on a rectangular. So that means if the true break is here, then for all the rectangular close by, it will be influenced by the true signal. So we need to clean out certain points that is influenced by the true signal, but it's not the break that we want to detect. So how to obtain that goal? Well, this idea is also very natural. So among all the candidates, we select the one that maximizes the statistic. So we first pick the one that maximizes the statistic here. And then we delete all the candidates that can be affected by this detected break. So all the other candidates that will be affected by this test statistic will be canceled. And from the remaining candidates, we pick another largest pair to maximize the statistic. And we repeat the procedure until there's no candidates left. So through this procedure, so this is the detailed procedure. I want to omit this because a little bit too much notations here. So through this procedure, we can determine the break locations as well as the time points. So this results I show here is just to say under this structure, the group's structure, we still have these Gaussian approximation results, which can help us determine the threshold. And based on this determined threshold, we can consistently estimate the break numbers, the break locations, as well as the break sizes. So using this method can be seen that this delta P here appears in the precision here. So delta P is the L2 norm of our signal. So that is to say this if all the series jump simultaneously within this for this gamma K, this delta P will be proportional to P. So that is to say if the dimension P increases, this precision will increase as well. Okay, here is some simulation or some real data application that we use this testing method. So we apply this testing method on COVID-19 cases in the US. And here is the result. So we roughly cluster the data into several regions and apply our method to detect the potential break locations. So well, in general, we can find 3 locations, for different regions, the detected break locations differs for different locations. Say, for example, the first break location we figure, well, it might not be that clear from this picture, but the real data that we detect, we figure that for the first break locations, the west and the northeast, the break locations seems a little bit before the rest of regions, the Midwest or the South. And also for, so this corresponding to the first outbreak of COVID-19. The second break corresponding to the Delta variant, and the last one corresponding to Omicron outbreak. So it seems that we can figure out all the 3 locations based on this method. And for different regions across the US, there is a slightly different phenomenon for different locations. So next I want to say some summary of this L2 type Moson statistic. So essentially, we can construct our test statistic through this maximum norm, and it can be approximated by some Gaussian random vector and with this maximum. And based on this Gaussian approximation, we can determine the threshold. If the test statistic exceeds the threshold, then we reject the null hypothesis. We are able to incorporate cross-sectional dependence. So when cross-sectional dependence is involved, similar Gaussian approximation result still holds. The cross-sectional dependence that we need to impose is that if the location they are far away, then the dependence should decay. And for this L2 two-way Moson statistic, well, we need to aggregate our data well within some neighborhood BL. And I forgot to mention here, when we construct a statistic with the neighborhood, we need to standardize by the break size. And after such standardization, we can still construct this Gaussian approximation. And based on this Gaussian approximation, we can perform the hypothesis testing. And the last thing I want to mention is that, well, because this is an L2-based statistic, well, we actually favor a larger dimension P. But because as we can see from the previous results, when the dimension P increases, the testing precision will actually increase as well. And related to a question that is asked before about the bandwidth selection of B, this is very critical for this change point detection in general. So the bandwidth selection here, Bn. So in our setting, we always, so here we assume the bandwidth Bn, well, within a neighbor, we should not contain, well, more than 1 breaks. There should only have 1 break within a window size Bn. And as can be seen from the results, that the larger the bandwidth, the better the precision, because from the consistency results, if the Bn is large, it seems the precision will be better. So there is a question about how can we pick a proper B. The method that we are currently using here is that we start from a relatively small bandwidth, and then we keep increasing it. And you can imagine that if the bandwidth is too large, the number of breakpoints that it reported will drop down when the bandwidth is too large. So we stop when the bandwidth is too large, when the break number change. So this is what we are using currently. But there is some other methods about bandwidth selection for this Moson type of statistic. Like there are some results about the multi-scale Moson statistic, which is to say that instead of looking at this test statistic here with instead of looking at the test statistic with a fixed bandwidth B, well, we can look at the multiple bandwidths. And we take the maximum over the multiple bandwidths as our new statistic. So essentially that is to say we look at several bandwidths together. That is another way handle the bandwise selection issue, but there's some drawback about all those methods that I mentioned. So this is still a very important question to explore about what's the best strategy to find the bandwise. So we currently is using the bandwise through using multiple bandwise and pick the one that does not change the break numbers. The larger possible bandwidth does not change the break length. Okay, so this is about the test statistic, and that's all for my presentation. Thank you.
Somewhere in here, there must be a condition on how big the breaks are in order to get consistency.
Yes.
So, but did you give us a little?
Yes, that's right. So let's go back to the relatively simple situation where we do not involve too many notations about the locations. So here is the requirement about the break size. Here, yes. So here is the requirement about the break size. So gamma k corresponding to the jump vector. This is the L2 norm of the jump vector, and we assume that this at least the jump vector need to exceed the threshold here. So the right hand side is the threshold. So it is p times log n a quarter times divided by bn, square root of bn. So that is to say, if B is large, the bandwidth is large, this so we allow the signal to be relatively weak. And also for the dimension P, if as we mentioned, if all the series jump simultaneously, the left hand side will be A. The jump size for each coordinate is A times square root of P. So that is to say, if the P increases, the requirement for each location, the jump size of each location actually decrease as well. So if more series jump simultaneously, the requirement for the jump size of each location decrease. Is this making sense? Okay, Sam. Yes.
We focused on the L2 sum. One could also consider L1 sum of components here to sort of take care of outliers.
That's right.
There's something.
I'm actually curious. What are you thinking about, the absolute summation or just the directly summation? Oh, yeah, absolute summation is more difficult. If directly take summation, it's easy. But if there's an absolute value there and we take summation over the dimensions, it's quite challenging because of this absolute value.
Also, you focused on change points in the mean, but also there could be change point invariances and other stuff.
Exactly. So when there is like a change in the variance, probably you should we need to like consider this say vector z transpose, and then it will becomes well, of course, z minus z bar times z minus z bar as a covariance estimation at each point, and it will centered at the covariance sigma. And if we assume the sigma there is a change, it will involve some kinds of quadratic statistic. So and it will be the mean change for a quadratic statistic. So it will be different from here, but yeah, it will be more complicated for the covariance situation.
So in this setup, each of your time series has essentially the same number of observations, and with the rescaling that happened, it's sort of a measure of how dense the observations are within some, let's say, window from 0 to 1. Do you have an idea of how these power results change if certain time series have essentially more frequent observations compared to others, or if the n within each series goes infinity faster or slower than others?
A good question. So currently in our setting, we assume all the series, the frequency of observation, they're the same. So if they differs, the B, the bandwidth. So currently the bandwidth for each dimension, we use the same bandwidth. If the situation happens like you suggested, probably the bandwidth for each dimension should be different. That will accommodate for the situation where it's less frequency or more frequency so that they are comparable.
Hey, thank you. I said too, your time varying mean has a smooth component and a jump component. Was there a condition on how smooth it has to be?
Yeah, surely. So depending on the, so you're absolutely correct. The smooth variant part so when we construct the statistic, so like here in the very beginning, so when we construct the statistic using this, the left average versus the right average, and look at their difference, it will contain the smooth variant difference. And this will determine based on how smooth the function is. And of course, if this difference for the smooth variant part is small, then the requirements will be weaker. If it's larger, then the requirement will be stronger. Essentially, if there is the smooth variant function is just a piecewise constant, then the requirement here will be the weakest. But if there is relatively not that smooth, then by aggregating over dimension P, this noise will accumulate to the level of P, which can be very large.
So what happens in terms of correlation from spatially distant regions? Because I know you have the assumption of decaying spatial correlation.
Mm-hmm.
So in some settings you could have correlation from very different regions. I don't think it has a very big impact on the results you showed. I don't know if you thought about that.
Can you say it again?
If you have 2 different spatial regions
Uh-huh.
that are correlated with each other.
Ah.
Right? So how does that impact some of the things?
So currently we are assuming that for regions that are far away, they should be approximately, independent essentially. But if, as you mentioned, but actually that is something that might happen. That although 2 regions they are very far away, the dependence can still be strong. So this situation, we haven't solved those situation, but that's some question I think it's worth exploring, especially like the COVID-19 situations. Say some cities that is very popular, probably those although they're far away, but there's some direct flights. Probably the correlation can still be very strong. That's a very point, but that might involve some technique that we need to think of.
2 questions. One is clarifying one thing. So for the clarifying question on the bandwidth, and that just like empirically what you observed, my understanding is correct that as the bandwidth grows, you have lower restriction on power, but at the same time you have a higher chance that several breaks will go within the bandwidth. So empirically, would it be correct to say that as you go from sort of smallest to largest, the number of change points detected grows at first and then sort of goes?
Yes. That's exactly what we figure out currently. So we just stop when it drop down.
Yeah, okay. My understanding is correct because it's also a combined signal across the time series. So as the dimension grows, as you get more time series, you get better performance. But I think in the statistic, we use those lambdas. And the lambdas, if my understanding is correct, have to be estimated based on the noise and the lower range dependence. And my intuition is that estimating that as the series grow is not going to be very good. I'm just wondering how those 2 balance out.
A good point. Yes, you are correct. The lambda is the long run variance for each coordinate need to be estimated to to handle those different variance for different locations. And the estimation of this long run variance, well, luckily we don't need to estimate a P by P matrix. We just need to estimate P parameters because we just need to estimate long run variance for each location. So theoretically speaking, in order to make this algorithm work, we just need to bound the maximum norm for the difference. So that is to say, we just need to control the maximum of the sigma hat versus sigma. They are small, then the theory will go through. But I guess if well, so that's probably the reason why the P increases, our performance is getting better.
So, you told that in situations where only a few series makes a jump, there the infinity-based method will probably perform better, and where like a lot of series are making simultaneous jumps, this L2-based method will perform better. So I was thinking, have you compared the power condition of like L infinity and L2 based? Because for the L infinity based method as well, as the number of P increases, then it will be easier to detect. And while I understand that for the L2 based method, like you are just summing these things up, but your threshold should be also more stringent because you have much more noise when you are adding like P.
Yes, so when if I understand correctly, you mentioned that if we aggregate the P dimension using L2 norm, the noise also accumulate, right?
Yes, and so like when you are comparing these two methods in terms of like the power, then how do these compare, and do you have any confidence about that?
Yeah, that's right. So yes, as you mentioned, that when we consider the L infinity norm, the noise does not increase that fast as well. The signal does not take advantage of the increase of dimension P. But when we use the L2 norm, the noise and signal, they both increases. But the thing is the signal increase faster than the noise. So the signal increase at the level P, the noise increase at the level square root of P. So therefore, we still take advantage by this aggregation. So essentially for this L2 norm, we kind of have a faster increase of the signals. So comparing the signal versus noise, we are still taking advantage of a larger dimension.
Let's thank our speaker again.